Welcome to The Explainer, everyone. I am absolutely thrilled you're joining me today because we're about to dive into a truly foundational journey. We're stepping into the surprisingly high-stakes world of measurement. I mean, think about it. Whether you're baking a cake, building a massive suspension bridge, or administering life-saving medication, the numbers you rely on literally define the reality you create. But what happens when those numbers lie to us? Well, today, we're going to unpack exactly how we capture the true, undeniable value of the physical world around us.
Okay, so here's our roadmap for today. We'll start with the measurement dilemma, then tackle accuracy versus precision, explore why measurement matters, talk about choosing the right tool, and finally, look at deriving entirely new quantities.
All right, let's jump right into part one, the measurement dilemma and the real danger of false measurements.
So let's start with something we all do pretty much every single day, observing the world and just trying to quantify it. We all know that feeling of making a rough, eyeball estimation. It can be a really fun, playful way to communicate scale, like saying something was this big. But in serious fields like science, manufacturing, or engineering, guessing just isn't going to cut it. Which brings us to a really crucial question. How do we actually avoid false measurements? Like, why do we measure things in the first place? And more importantly, how do we absolutely prevent getting it wrong? Well, the answer lies in incredibly strict definitions.
Moving right along to part two, accuracy versus precision, and untangling these two concepts.
To avoid those bad measurements, we really have to untangle two words that people constantly mix up in casual conversation. But trust me, they mean completely different things in the scientific world. Accuracy is all about correctness. It's about hitting your specific, true, or accepted target value. Precision, on the other hand, is about consistency. It's the repeatability of your measurements, regardless of whether they're actually close to that true target. Think of data collection kind of like a game of darts. Every single time you measure something, you essentially face four possible outcomes. You can be accurate and precise but not accurate but not precise, or, and this is the absolute worst-case scenario, neither. It's such a fantastic mental model to just keep in your back pocket whenever you're staring down a spreadsheet of data.
For example, when a cluster of data points centers beautifully right on that true average value, the literal bullseye, you have high accuracy. But a highly precise cluster? That simply means all the hits are grouped really tightly together in a repeatable way. So if that tight little grouping is nowhere near the center target, it's highly precise, sure, but it is wildly inaccurate.
Let's look at part three, why measurement matters and the real-world stakes involved.
Now, you might be wondering why we're being such absolute sticklers for these definitions. Like, is this just some boring academic exercise? Far from it. Accuracy and precision are quite literally the backbone of modern society. They heavily impact research, medicine, electronics, manufacturing, the whole shebang. The difference between an accurate measurement and a merely precise one can literally be the difference between a product working flawlessly and a total catastrophic failure.
Take medicine, for example. It's kind of funny to imagine a cartoon character just recklessly mixing up volatile chemicals, but in a real-world hospital, inaccurate doses can seriously harm patients. You simply cannot afford to precisely deliver the wrong amount of a powerful drug. That turns a potential cure right into a life-threatening crisis.
And the exact same logic applies to engineering. In everyday household appliances and electronics, inaccurate measurements might literally spark a fire. When you're dealing with things like voltage, wire thickness, or circuit spacing, being off by just a tiny, microscopic fraction, we're talking even 0.01, might lead to absolutely disastrous results.
Which brings us to part four, choosing the right tool, based on scale and application.
Since we know for a fact that bad data is dangerous, we have to choose the right measuring instruments. It's a classic showdown, really. The everyday standard plastic ruler versus the highly specialized metal micrometer. Now, both of them measure length, but they belong in completely different universes of precision.
So you'd use the standard ruler for macro objects, right? Situations where a smallest scale of centimeters or millimeters is perfectly fine. But when your work demands extreme precision, you absolutely need a micrometer. It lets you measure outside dimensions, inside dimensions, and even the depths of objects down to incredibly tiny fractions of millimeters. When you compare raw data from an experiment, the difference is just stark. A student using a standard plastic ruler can really only estimate measurements, say 27.9 or 28.0 millimeters. Meanwhile, a micrometer confidently spits out values like 28.246 and 28.244 millimeters.
That is 3 decimal places of precise consistency, compared to just broad, rough estimates.
And finally, part 5, deriving new quantities and building complex measurements.
Once we've gathered those highly accurate base measurements using the right tools, we actually unlock the next level of scientific analysis, the derived quantity. This happens when you mathematically combine 2 or more of those base measurements to calculate an entirely new property. For instance, you don't actually measure area directly. You measure length twice, and then you derive the area mathematically.
Think of it kind of like building a digital avatar in a video game. You don't just click a button that says character, you combine height, width, and individual features to build the whole thing. The base measurements of length and height are your fundamental building blocks, and that derived quantity of area is your final structure.
And this is exactly why derived quantities are so unbelievably powerful. Incredibly complex physical concepts, things like force, energy, pressure, and density, they're really all just brilliant mathematical combinations of simple base measurements, like mass, length, and time. If you want to find speed, you just measure length and time. It all traces right back to the absolute integrity of those initial base measurements.
So I'm going to leave you with this rather provocative thought. We already established earlier that a tiny 0.01 error in a base measurement can literally cause an electrical fire. So how disastrously magnified does that tiny error become when we start multiplying it to build complex, derived quantities like force or pressure? If accuracy and precision are lacking at the foundation, well, the entire mathematical house comes tumbling down. Thanks so much for joining me on this explainer, and remember, always keep demanding precision from the world around you.
Since you reached this far, if you enjoy this video, give us a like and share this to your friends. Always remember, like Sir Cedric always says, learning is forever. See you next time. Bye.